Hello world, it's Siraj, and we're going to talk about something a little different this episode called the blockchain and how it can be used to improve AI. The World Wide Web has only been around for a couple of decades, and it's grown orders of magnitude in that time. Billions of machines are coming online as internet-connected devices, mainly phones, are distributed globally. We've collectively defined a standard for how they should communicate, called the Internet Protocol Suite. At the lowest level, the link layer puts data on a wire. Then the internet layer routes this data, the transport layer persists it, and the application layer delivers abstractions of it in the form of the apps that we all know and love. This has worked pretty well for our machines, but there's a missing layer, a layer of smooth, refreshing mayonnaise. Now, where's the protocol to let them exchange not just data, but value? The main way it's done right now was invented pre-internet, and it requires using a centralized clearinghouse, so machines have to sometimes wait for days for a payment to transfer from one to the other. But in all other aspects, they communicate with each other at a mind-boggling rate. What if they could send each other micropayments in the same way to meter resources like electricity and storage space and computation, all without having to wait for a middleman for a payment? He stole my painting, didn't he? No, Bitcoin and other cryptocurrencies solve this problem. They act as a fifth protocol layer for value transfer, and their underlying technology, called the blockchain, makes this all possible. The blockchain, for the first time, allows machines to agree on value transfer without having to trust a central authority. In the real world, if I create a painting, I and only I own it. But on the internet, if I created a digital painting, you could just copy it and then we both own it. There's no way of proving who owns it without using a central server that records that ownership. We have to trust the server, the middleman. But the blockchain lets us reach consensus in a decentralized way that prevents a bad actor from falsely claiming ownership. Not just for paintings, but for any asset like Bitcoin. But how can this be used to improve AI? Well, one use case is giving both datasets and machine learning models a reputation. How do you know that the data or the pre-trained model that you're using is quality, that they haven't been tampered with? You basically have to trust a single source, unless you use a blockchain. DeepMind is using a blockchain to create a publicly verifiable auditing system for healthcare data. It records every interaction they have with sensitive patient data, so patients know if a piece of their data has been used and a reason why. It's write-only, so once a record of data use is added, it can't be erased. That means patients can verify that no one has tampered with any of the entries. Hi. Another is a peer-to-peer network for training models. Instead of training your AI using services like AWS and Google Cloud, imagine a system where people could just rent out their spare computing power to help train models and get paid in TensorCoin, or even a company that is run entirely by AI. Blockchains are decentralized databases, so if an AI lives on a blockchain, no one could control it. It could live as an independent entity on the web, paying for whatever services it needs. Just define an initial set of rules and set it free. One example would be a self-driving car network run and maintained completely by AI. Yo! Let's build our own simple blockchain in Python to understand more about how this incredible data structure works. But first, he lives in you. He lives in me. Only you get access with your private key. First, let's define what a block is. For simplicity's sake, let's say that each block represents a single transaction, a value transfer between two machines. We'll define the blocked object in its own class with a set of important attributes. The index represents its ordering in the chain of blocks. Its timestamp shows when it was created. It will store some data that is defined by the sender, as well as two hash values, one for the previous hash in the chain of blocks, and one for its own hash. The reason a block needs a hash is dual purpose. It gives it a unique ID, and it verifies the integrity of the data. We'll use the popular crypto hashing algorithm called SHA-256 to help generate a 256-bit signature from the other attributes for each block in the hashing function. So how is a block generated? Well, the user provides some data in their transaction, so we'll use that as the only parameter in the generate function. And since each block is ordered, we've got to fetch the last block. We'll use the last block to help define this block's index as well as its hash. We'll also give it a timestamp so we know when it was generated. So each generated block points back to the previous block by storing its hash. It's a chain of blocks, a blockchain. The first generated block is called the genesis block, and we'll hard code it in by predefining its attributes in its own function. Then we'll use it to initialize the blockchain, and we'll store it as an in-memory list. So remember how I said that a block's hash serves as both its identity and verifies its integrity? We can use the hash to determine if a newly generated block is indeed valid. Given a new block and the previous block, which is the last block in the chain, we can first check to see that it's got the right ordering via its index. Then we can check if its previous hash attribute matches the already verified previous block's hash. Lastly, we'll calculate the hash for the new block and make sure it matches the hash that it stores. If it passes these checks, it's verified. Assuming all nodes store a copy of the blockchain, we need a way of choosing which blockchain to use in case there are conflicts. Let's say two nodes generate the same block number. Our solution will be to choose the chain that has the longest number of blocks. Since it's been around longer, it's more likely to be the true blockchain. Given a new blockchain, we'll check if it's valid programmatically, and if it has more blocks, we'll replace our blockchain with a new one. Else, we can just reject it as invalid. Since each node stores a copy of the blockchain and blocks are constantly being generated as transactions occur, we need a method of keeping each node's blockchain in sync. To do this, each node broadcasts to all the others whenever it generates a new block. When a node connects to a new node, it queries for the latest block, and when a node encounters a block with an index larger than its current known block, it can either add the block to its current chain or query for the full blockchain. And so the way we can encapsulate a node so that both the user can query it as well as other nodes would be to create an HTTP server. We could create endpoints for a couple of actions that a user could take. One would be to list all the current blocks in the blockchain. Another would be to create a new block given some data as a parameter by the user. And another could be to list all the other nodes in the network or even add new ones. So the user would control the node via HTTP requests, and it would communicate with other nodes via peer-to-peer WebSockets. So that's our simple blockchain. It's very minimal and doesn't include all the features that Bitcoin's blockchain has, but hey, it's an example. However, crucially, there is one key feature that I left out that we should talk about called the proof of work algorithm. Our naive blockchain is vulnerable to what's called a Sybil attack. This is when a bad actor creates a bunch of nodes to get disproportionately large influence over the network. Once he has control of at least 51% of the network, he can validate his own transactions. He can spend the same money more than once or double spend. To prevent this, Bitcoin mining nodes complete a series of really computationally expensive calculations to approve each transaction and get paid in Bitcoin for their computational work. In order for a newly generated block to be accepted by the network, miners must complete a proof of work which covers all of the data in the block. At least 51% of nodes must reach consensus that a new block is valid for it to be added to the blockchain. And so a bad actor has to have more computing power than half the network. For Bitcoin, this amounts to more computing power than the 500 fastest supercomputers in the world combined. No one has that much computing power. Not even you, Mark Zuckerberg.
Jarvis also helps me get ready in the morning. Hell yeah.
And that's why the Bitcoin network is still secure, even with a $50 billion market cap. Every week, new blockchains are being created with different use cases. There is so much to talk about when it comes to the blockchain, and we've barely begun to explore what happens when we use the blockchain as a way to improve our AI. It can help us verify the quality of our data and models, create peer-to-peer exchanges where we trade them with each other, create never-before-possible businesses where we monetize different aspects of AI development, and even create independent organizations run entirely by AI. Last week's coding challenge winner is Charles David Blott. He used an earthquake dataset to predict the magnitude of future earthquakes given features like latitude and longitude. He built several optimizers from scratch for his neural network, including atom, momentum, and stochastic gradient descent. All three are viewable in his graph. Awesome work, Charles David, Wizard of the Week. And the runner-up is Parminder Singh, who also implemented all three optimizers from scratch to find the local minima of a function. This week's coding challenge is to write a simple scheme to encrypt a dataset so only someone with its private key can access it. Check out the README for all the details, and I'll announce the winner next week. Please subscribe to become a programming wizard. Check out this video right here, and for now, I've got to invest in Ethereum, so thanks for watching.